the Hamiltonians, okay, the atomic Hamiltonian only contains the zero order Hamiltonians, the Hamiltonians for electron repulsions, and the Hamiltonian here uh, from the couplings of spin and the orbital angular momenta. So we can have here these additional terms, okay? The Hamiltonians for external magnetic fields, okay? So we can see here both the orbital here, okay? So this is sum of these orbital and the spin magnetic moments. We can write like this, okay? So using this, okay, some of these two magnetic moments operator here. So we can have okay, this is how we define. We can relate with the vector of angular momentums, the total angular momentums here, and also the spin vector here. Okay. So from here, okay, we also can consider the first order perturbation theory, these crude approximations, okay, to find the energy of interaction with applied magnetic field. So we can use this first order perturbations, okay. In fact, we can use higher order, okay, to get more accurate result in our calculations. Here we use this crude approximations, okay, in order to find this interaction energy with external magnetic field. So we can use here this what we call this zero order wave functions, okay. So once we use the zero order function, we will get actually only the first order energy corrections. Okay, so this is the first order perturbation theory. So we get here this energy, the approximate energy, okay, for EB. And so for weak magnetic fields, okay, we can from this, okay, we can have this magnetic field interaction energy here, okay, which depend only on this mj, and this lambda J factor, okay, for fixed value here, okay, J, L, and S, but with different value of MJ will give different EB here. Okay, with same here J. Okay, let's say for the P, this triplet P2 with the same L, J here, and S. Okay, but different NJ will give different energy. So this energy will split into 5 different energy with different MJ. Okay. So from here, okay, when we introduce the electric field, the energy, we can see here split into 2J plus 1 state. Okay, this is 2J different state, 2J plus 1 state. Okay, so the J here is 2, so we have here will split into 5 different state here. Okay, 2J plus 1, 2 times 2 plus 1. Okay, here each having different value here, mj. So we also can proceed this, okay, by adding different couplings, okay, between probably between what we call this L and between nuclear spin angular momentums, okay, with the J, okay, because we know nucleus also has its own angular momentums, so we also can couple this, okay, nuclear spin angular momentums with the electronics total angular momentum J, okay, to get the total angular momentum F. F is the coupling between the spin, the nuclear spin, and the electronics angular momentum J, the nuclear spin I, the nuclear spin angular momentums. Okay, this nuclear spinning by its own, so this is also its intrinsic angular momentums for nucleus. So you can read this, okay, which is not here, okay, for different coupling. So for today's lecture, okay, I want to finish this before before we start with a new chapter on molecule. So basically here, okay, I want to introduce this Hartree-Fock fields consistent methods, okay, Hartree-Fock consistent field methods. These topics, okay, covers in depth in advanced physical, advanced quantum chemistry. So here, okay, I will only give briefly, okay, introduction on this topic. So this Hartree-Fock, okay, Hartree-Fock self-consistent. I think you heard this in first year or second year, okay, in your physical chemistry course. The Hartree-Fock method, okay, use anti-symmetric wave functions. Anti-symmetric wave function as its, okay, trial function. So we have here variation integrals. So this is the Hamiltonian operator. So so this trial function, okay, is the anti-symmetric slatted determinant. Okay, so the anti-symmetric trial functions is the slatted determinant. Okay, what we found, okay, from the perturbations. So the Hartree-Fock method is the variational method. So this is the anti-symmetric slatted determinant, which is the linear combinations of spin orbital. Okay, this spin orbital, linear combination of spin orbital. Okay, so the trial function we use using these variational methods, okay, and this Hartree-Fock based on this variational method, okay, where the trial function here is the linear trial function, and the linear trial function here is the anti-symmetric slatted determinant, which is the linear combination of this spin orbital here. Each of these metric elements here is the product of the spatial orbitals and the spin function, which is called the spin orbital. So, and when we have this, okay, Hamiltonian operator, okay, for many electron atoms, we have this interelectronics interaction terms here. Okay, we can prove the energy here. Okay, for the closed shell, we consider here. Okay, for simplicity, we consider here closed shell system. Okay, in which here we have here n half of these doubly occupied spatial orbitals. Okay, so in case for the open shells, okay, we can use this n spatial orbital. Okay, so we have here 2 plus, sorry, this n electron here. This is n electron here. Okay, this n electron here, we have here, this is n electron. We use this Slater determinant, as I said. We have here Slater determinant and factorial here. Okay, this is n electron. We substitute into these variationals integrals. Okay, we end up with this total energy. So the total energy here, okay, we consider for the closed shells, okay, for the n, the number of electron here is half, because for the n atomic orbitals or the n molecular orbital, this also can be applied for molecule. Okay, each of these atomic orbitals or molecular orbitals here, okay, we can have here 2 electrons with different spin occupied in this atomic or the molecular orbitals. So for the n orbitals, okay, so n electron here. So the number of orbital here is n half. Okay, this n orbitals, so the number of electron here is n number half. Okay, so okay, so we have here n half for the closed shells here. Closed shells n half doubly occupied spatial orbitals. Okay, so occupied orbitals for the closed. Okay, for just for the sake of simplicity, we can use this models, the closed shells atoms. Okay. Now this energy here, you can see here we have 3 components of energy. This is the hydrogen light orbitals energy. Okay, you can see this is the hydrogen. This is Hamiltonian operator. Okay, this one. The kinetic energy for 1 electron here, the interaction energy between electron and nucleus. So this is the Hamiltonian operator. Okay, we have here, this is H0, this is Hamiltonian operator, the hydrogen likes Hamiltonian. So this is what you learn, okay, the repulsion one, okay. OH prime, this is our perturbations. Okay, if we are discussing here in terms of perturbation, so this is our perturbations. Okay. So you also can relate this, okay, with the perturbations. The Hartree Fock is the variationals, okay. Later, I will show you, okay, how we can relate the perturbation. They are actually identical, these 2 approaches, okay. The variationals and the perturbations, okay, to get the approximate energy. And okay, we have here, so the repulsion here, you can see this is the repulsions. Okay, so this is the hydrogen-like energy. Okay, if you have two electrons, okay, of course you have this, the Laplacian operator here, J here, is 1 and 2. So you have this 2, Ij. So you can, for helium, okay, you can have here I2, correct? I1 and I2. The summation here goes from, you can see here, this electron. For 2 electron is 1 to 2 for helium. This as well, from 1 to 2 for helium, 2 electron. Is 4 electron, is 1 to 4. So we will get here 4I here, with 4 electron. So this is the hydrogen-like energy you learn in physical 1, which you can solve, okay, analytically the Schrödinger equation, second order differential equations. So the components, we have here this energy, okay, due to these interactions between electrons. So the Ij here, okay, for 2 electron here, okay, for the ground state, okay, you have seen this. Electron 1 in 1s, this is the zero order wave functions, the correct zero order wave functions. Okay, this is an acceptable wave functions because we cannot distinguish these two electrons. Both here occupy in 1s state. So the interaction here, when we introduce, we only can get the one component of energy, which is the J11. Okay, you can refer back our previous lecture using the perturbations. You can get this similar total energy. Okay. Okay, where here is the zero order, the sum of individual hydrogen-like energy, E1 and E2, zero order E1 and zero order E2, plus this E1, okay, in terms of perturbation. So the J here, this is the E1 here. Okay, so this is the E1 actually. Okay, you can prove this, okay, when we substitute this one. Okay, as I said earlier, we have this Slater determinant for the ground state configuration. We have the Slater determinant, which is the combination with this symmetric will combine with anti-symmetric, right? Okay. But this Hamiltonian operator, the coordinate is the spatial coordinate. It's the spatial coordinate. This is not the spin coordinate. The spin coordinate only depend on the ms, the component of spin. Okay, where the plus half or the negative minus half. So the effect here, the Hamiltonian here, okay, only here affect the spatial orbitals. Okay, this spatial orbital, this operates on this function only, not this function. Okay, so you can actually take this out from these integrals, the spin part here. Okay, so this spin doesn't affect this total energy. So this is the spin part here. only the spatial part here. Okay, so this is the slated determinants. Simply here written as 1s, okay, we spin up, 1s we spin down. Okay, this is the simplest form of slated determinants. Okay, this anti-symmetric slated determinants. Okay, so the Hartree Fock use this slated determinants. Anti-symmetric slated determinant. Okay, when you substitute into this one and this one, okay, oh, sorry, here, using this Hamiltonian operator, which can be expanded here, okay, in atomic units for helium, okay. You have seen this before. Electron 1 kinetic energy for electron 1, kinetic energy for electron 2, okay. And then potential energy, attraction. Okay, the Z here is 2 for heliums. Electron 1 with nucleus, kinetic energy, attraction between here, electron 2 and nucleus. And negative charge will get here, positive charge here. The repulsion between electrons, these two electrons. Okay, you can here substitute into this. Okay, and using the definition of this one, okay, you can show you this is I1 plus I2 in G11. So if we consider the one as the excited state configurations like this one, okay, this is not the correct one, 2 electron here, okay, because they are identical, you must have here, let's say one of this combination. Okay, when you substitute here, okay, sorry, here, using this Hamiltonian operator, you can get here this energy I2, okay, J11 and minus K11. Using these definitions of what I call this Coulomb energy and this exchange energy. Okay, we already solved this one using perturbation, and you'll get this similar answer for the total energy. Okay, so next you can see this one. This is the spin orbital. This is our trial function. How we are going to get this spin orbital, the spatial orbital here? If you guess this one, that means you also need to guess this one, the spatial orbital of this spin orbital. Okay. In modern quantum chemistry, all these atomic orbitals, okay, these atomic orbitals have been already designed, devised by quantum chemists, okay, which include several parameters here. You can use this Slater type orbitals or the Gaussian type orbitals in modern quantum chemistry. Okay, you will learn this in details in advanced physical chemistry. Not advanced chemistry, advanced quantum chemistry course. Okay. So we can have this, and this is our gas function for the atomic orbital. Then we can use this Hartree-Fock self-consistent method. This called self-consistent method. By guessing here the atomic orbitals, whether the slatted types or the Gaussian type orbital here, this one. Okay. So we can find the orbitals energy for each of these gas orbitals. In this case is the atomic orbital. Okay. By here guessing initially here this using the orbitals that already being designed. This one. Okay, you can refer in the website. There is a link, okay, showing all the hundreds designs basis functions, Gaussian types of orbital or the Gaussian type of the basis function. So this one, if you notice here, this is the linear combination. If you have this simple one S2, we have the coefficient here in front here. Okay, so this one. In the Hartree-Fock, this will be optimized. Okay, the orbital exponent here already been optimized, okay, by quantum chemists. Non-linear optimizations for the parameter inside of this. Okay, using this Hartree-Fock method, self-consistent, to get the best value of this C1 and C2. Okay, so and then, okay, from here you can get the best value here for the coefficients from this one differential equation, these Fock equations here. This is one differential equation, this one electron differential equations. Okay, this is not the multi-electron differential equations. To find the orbital energy for each spin orbitals, this orbital, each of these orbitals, and each of these orbitals. Okay, for one electron, one individual electron. So we need to guess this in order to know this one and to know this one. Okay, once we know this one, we can solve this Hartree, this Fock. This is the Fock operator. We know that this one, and we know this J and K, we will know this Fock operator. We know this Fock operator, we can solve this one electron differential equations to get this orbital energy and this corresponding orbitals, atomic orbitals. If for molecule, this is the molecular. Okay. When we solve this, we know this Fock operator, we can solve this one, we can get this new phi. we can use this new phi to get this new j and k. Okay, you get this new j and k, you can get this new Fock operator, you can solve this, the next cycles or iteration in our calculation. Okay, to get the another new, okay, the coefficients, let's say this, we have only two, let's say only two. We use the combination here, only two basis function, which is 2 by 2 Slater determinant. So the C1 and C2, you can get this value, okay, in our first iterations, the next iteration, until this value converge. Okay, and you must set, okay, initially, okay, that you feel that your conversion is good. Let's say up to the 6 decimal points. Let's say we have the 8, this is number here, 1, 3, 4. Okay. So if you satisfy in your calculation, you only consider up to this 4 decimal points. So you can stop your calculations. Okay. So this convergence, okay, at the same time, the energy also will converge this orbital energy. Let's say for electron 1. And the conversion of the energy is faster compared to this convergence of this one, this orbital energy. These orbitals. The orbital depend on this coefficient, right? So in most calculations, the convergence of this reach, okay, earlier than this orbital, which is the combination of this linear combination of these two orbitals. Okay, what I mean here, this orbital, if this is pi 1, this is pi 2, okay, in these examples, for simplicity, we can use the helium. This is 1s1. This is 2s2. And this is 1s2 and 2s1. Okay, we have done this one. I will give some exercises on these topics. The Hartree Fock. Okay, this is self-consistent means, okay, the Hartree Fock the calculations for convergence for both the orbitals and the energy, orbital energy, self by its self-consistency. Okay, so this method is called self-consistent fields procedure. Okay, and from here you using this Koopman proposed this idea. Okay, name after him, Koopman theorem. Okay, so the ionization energy, okay, actually is the negative of this Hartree Fock energy, Hartree Fock orbitals energy. So this is the ionization energy. I think you also seen this before, heard this before. Okay. So I want to finish this chapter, and this also can be, okay, shown, corroborates, okay, using the quantum mechanical wave functions, okay, spectroscopies. Okay. Spectroscopies, okay, use this rule, selection rules, to determine whether the transition is allowed or not, forbidden. Okay. okay, using these rules. And these rules also can be determined quantum mechanically. I will not show this, okay, in this course using the time dependent, okay, time dependent method. Okay, what you learn, okay, so far is the time independent, okay, which the Hamiltonians, you can see the Schrödinger equation does not depend on time. We approximate that time independent Schrödinger equations using the variationals and the perturbations. Okay, for this transition, you need to use the time dependence methods, okay, to show these rules, whether the transition law or not. So spectroscopists here use these selection rules, okay, and always here we can apply this for the light atoms, and sometimes fails for the heavy atom. This is only rules, like the Hans rule. Okay, sometimes it fail. Okay, to explain the transition between the state, between levels, energy levels. So we can use this for the light atoms, the delta A, a delta L, the total, the difference of total angular momentum, the difference of total spin, and the difference between the total angular momentum here must obey this 0 plus minus 1, 0. Okay. And J also, the total here, 0 plus minus 1. Okay. And this is for the more one electron transitions. Okay. Mostly we find, okay, it's the one electron transition, which means the difference of these electrons, the orbital angular momentums delta L here, okay, the transition between different electronic configuration here for the one electron transition is plus minus 1. Let's say 1s to 1s to s. Promoting here one electron here is allowed, okay, due to the fact that this rule for the light atom, okay, this I'm talking about this for the light atoms, we can use this rule where here the total L here, okay, oh sorry, this is the total L is not allowed. The total L here is 0, the difference. This is the total L here, okay, 0, 0. This is 0. Okay, so the difference here, this one, will be 0. One electron here, still in this, intact with this one S. We only promote here only one electron. One electron here to here. So we can use this one. Okay, the difference is not plus minus 1. How about this one? 1s to p. One electron here, one into the transition is from the 1s to 2p. So the difference here, delta L here, okay, for the absorptions, okay, the higher is possible. For the emission is minus, okay, the difference between the final state and the initial state. Okay. So you can get, so this is allowed transitions. So you can use these rules. When we use these rules, we must also consider this spin multiplicity. Light atoms, the delta S here, the spin multiplicity must be the same in order the transitions to be allowed. Same spin multiplicity. Okay, let's say, okay, I want to show you this diagram. Within state is not allowed because 1s to p within state. So we cannot get this plus minus 1 this is not allowed. Or here, okay, for example, this one. Okay, how about this? We have this 1s 2s, right? And we have this singlet s. This is triplet s. Okay. About this, we must determine this delta S to be 0. So the transition only allowed between triplet S to triplet P. Triplet S to triplet P is forbidden as singlet P. Triplet S to singlet P is forbidden. Okay. So this because of this delta S. But sometimes for the heavy atom, the spin forbidden transition, okay, is allowed. Which is the transition between spin multiplicity is allowed for the heavy atoms. Okay. And also we have these additional rule here, section rule here. Delta L. Okay, from 1s to s here, triplet s to triplet p. So the delta L, of course, we'll get this here. Delta L plus minus 1. Okay. How about the J? Okay. When we consider the Russell-Saunders coupling, which is the spin orbit coupling, we also must consider this one, the J. So how about this one? Okay, this is 2 S. No, 2. This is 1. S is 1 here. The spin total angular momentum is 1. 1 plus 0 L0. So we have triplet S1. Let's say we want to promote this 1 electron. So this is for the 1 electron transitions from this to this one. Okay. Which here, this transition again is allowed. Okay, because here, the delta J here is plus minus 1. So this is J 2 minus 1 or 1 minus 2. So you get this plus minus 1. Okay, so you can read another example. So you can relate these transitions To find the frequency here, this is the wave number commonly used by spectroscopists to assign their spectra. Okay, the frequency, so this is wave number. Okay, the energy for in spectroscopy and also in quantum mechanical calculation, the most important is the difference. You only what you can read in the spectrum or spectra is the different energy. Okay, this you learn frequency. You can change the frequency to the wavelength. So in the spectra, you can read whether this in frequency, wavelength, or wave number. And this only can be found from the difference of energies. Okay. Between two energies. Okay. To find this energy, each of this energy, we must calculate quantum okay, what you can see, what you can interpret in your spectrum is only the difference of this delta E. This is what you know between this state. For example, there is a spectral line here, or atomic hydrogens here. Okay, this is on hydrogen only, one electron here. Hydrogen is only always doublet. Okay, one electron only. So the half is half. Okay, two half. Double state for the see. Okay, we have done for this topic, for this chapter. Okay, I'm going to start with molecules. So this is doublet. Okay, always doublet state. This is all doublet. Okay, the delta S is 0, correct? So the delta L here, D and P here, 2 and 1 here is plus minus 1. So you can, I cannot see here. This is 3 half and this is half. Also, the delta J here is plus minus 1. Plus minus 1, this is J and J. So this is allowed. Okay, you can try figure out the transfer. So we have done this. Now we are going to turn this molecule. This is the last. Okay, I hope I can finish this in 2 weeks before semester breaks. You also can make a request for extra class. Okay, during the semester break or study week. Okay. Okay, or at any time you feel free, available, so you can. Okay. Set the time. So molecules. What is different molecules and atoms? Molecules, we must start here with this approximation, the Born-Oppenheimer approximation. You also have, okay, here heard this approximation in physical 1. Many times this approximations. Okay, so we must begin with this approximation. Why we must approximation for molecules? Because of, let's say, we have this simplest molecule, the diatomic molecules, and we have this electron, one electron, these hydrogens, molecular ions. Okay, we have this another extra terms. Okay, this one. No. This is this one. Okay. Internuclear repulsion between these two nuclei, and also the kinetic energy for these two nuclei. Okay. In atom, you have only this one. Okay. If you want to solve this molecular Hamiltonian molecular Schrödinger equation using this molecular Hamiltonian, you can PK. Okay. If you want to solve this analytically, okay, which is not the differential equation. Okay. So, because we know this nucleus is much heavier than this electron, you can take this out. This kinetic energy. Okay, we consider this nuclei or nucleus in stationary state, considering only the motion of these electrons around these two nuclei. Okay, so the Born-Oppenheimer approximation based on the assumption, okay, due to the fact that this mass of nucleus is much larger than this one. Okay, we can ignore this, okay, in our initial calculations, approximations, and at the same time, when you consider, okay, this nucleus is heavy, you only consider the motion of electron. So the internuclear repulsion here, okay, can be set here as a constant because we fix the distance between this R alpha beta. So every time we fix this R alpha beta, okay, this one you can take this out. Okay, so you only consider the motion of this electron, which is the kinetic energy, the interaction electron between nucleus, the interaction between electron and electron, by fixing these nuclear configurations. Okay. This is the idea of the Born-Oppenheimer approximation, actually. So this is how we write. Okay, before we start with this approximation, this is how we write here by expanding these summations. Okay, for the hydrogen molecules, we have these two kinetic energy for two nuclei here. Hydrogen nucleus, we have two hydrogen nuclei. The kinetic energy here for two electrons. This is for two electrons. This is repulsion. No, this one. This one. Okay. This is electron. This one. And nucleus. Okay, we have here. This is alpha. This is beta. This is electron 1. This is electron 2. Okay, this is R1 alpha. This is R1 beta. Okay, you can draw this. Okay, all possibilities of interaction, and this between R. Okay, 1, 2 here. This is between R alpha beta here. Okay, from here you can construct this Hamiltonian operator, molecular Hamiltonian operator. Okay, if you have more electron, you can use this similarly. Okay, in constructing this Hamiltonian operator, you can draw this like this one. Okay, this diagram you can draw. Okay, and okay, now this is the molecular Schrödinger equation. So because of this, okay, based on these assumptions, okay, which is correct, solve this, this operate on this operate on this is the Vn, okay. This is the electronic Schrödinger equation, electronic Hamiltonian operator. Sorry. Okay. And a constant here, okay, acting on this wave function, okay, we'll get back this value, only a value here, number here, okay. So when you operate this, okay, okay, I will show you, okay, step by step. Okay, this one is U. This U. U is the pure electronics energy plus the VNN. Okay, this only constant. Okay, we get back this one. Okay, so this is U, the potential energy. Okay, now we want to plot this. Okay, this already defined. Okay, I already showed this one. This is VNN. So now, what is the most important thing here when we use this approximation to get this U? Okay, the most we need to solve this one, the pure electronics, which is this one. This and with this one, we will get this one. To get this pure electronic energy here. Okay, the second step in the Born-Oppenheimer approximation, like atom, we need to solve this approximately using variationals or perturbation. Okay, in this course, I will use variational methods. Because the electronic Schrödinger equation has these terms, inter-electronic terms. When we have these terms, we cannot solve this differential equation analytically. We cannot solve this on paper.